and I've been at NASA and in particular NASA Ames for 36 years now. I started at NASA right after my undergraduate, and the majority of that has been spent on space robotics. So just a little background of myself. I was born and raised in San Francisco. I'm one of 6 kids, the oldest. I got my bachelor's degree in electrical engineering from Stanford and my master's in electrical engineering from Santa Clara University. And that actually I did while I was already working at NASA. So as I mentioned, I've been here for a long time, 36 years. And I have a few hobbies such as horseback riding and fiber arts like knitting and weaving. The way I came across this profession was when I was in the 7th grade, we had a reading assignment. We had to read the local newspaper. And I came across an article called Women Engineers at NASA. And I had no idea what an engineer was or did, but I was interested in science and math and space. So when I saw the NASA, I thought, oh, that sounds really interesting. That sounds like the job for me. So that's how I then decided to take all my coursework to get me into engineering and lucked out and got a job. So the way I did find that job was I was recruited by NASA while I was a senior at Stanford. And I started as an electronics engineer in the information sciences division. I was working in what was called the photonics group. So we worked on optical sensors and processors. But my division was primarily software oriented. So I decided to learn how to program. And I worked on my master's degree part-time while I was working in the photonics group. I joined what was then called the Intelligent Mechanisms Group in '95. And the early work was geared towards robotic planetary systems. And I mostly worked on robot control GUIs, graphical user interfaces. So how do you command the robot? And then I also worked on visual navigation systems. So this means using a robot's cameras and the visual information that it collects for it to understand where it is. I also, as my career progressed, I started managing projects, and as part of my work, we did a lot of field testing. So what you see there on the left side is a couple of the field tests that we did. Oops, hang on. There we go. These are some of the robots that I've worked on over the years, all the way from this Russian-built chassis called Marzakad, where we did the avionics and the sensors and the software for, all the way to the most recent robot that I've worked on, which is Asterby robots, which are free-flying robots that are on the International Space Station and are currently active. So eventually the Intelligent Mechanisms Group became the Intelligent Robotics Group. And I became the deputy group lead in 2005. And mostly I managed the group's budget and contracts. But I continued working in project management and doing some systems engineering work. I did a 1-year detail, which is a temporary assignment at NASA headquarters in Washington, D.C., starting in 2010. And that was in the office of the chief technologist. Some of my more recent projects since I got back were and they've been mostly geared towards the International Space Station. So I worked on smart spheres, surface telerobotics, and Asterby. I got a Silver Snoopy back in 2015 for the surface telerobotics work, and that's a picture there on the right, me and Sonny Williams, the astronaut, getting my Silver Snoopy. And then I became the group lead for the Intelligent Robotics Group in 2019. So just in time for the pandemic. Okay, so that's a little background about myself. Let me share with you now some information. I'm going to mainly tell you a little bit about the Intelligent Robotics Group. We have a few projects that may be of interest, including Viper, which is a lunar rover. Let's see. All right. There we go. Okay, so move on from there. So the Intelligent Robotics Group at NASA Ames has gotten quite big. We've grown recently, like in the last 3 years, mainly in support of that major mission that we're working on, Viper. We're at approximately 50 researchers currently. 80% have advanced degrees. We generally get quite a few interns, or in the past we have. With the pandemic, it's kind of put a damper on things, and also with Viper being actually a flight mission, it's harder to find quality time for mentors to spend with interns. So we're more around like 5 or 6 interns a year the last couple of years. About 90%, or actually more than 90% of our work is funded by NASA. We do have some external funding sources, like some private companies that have Space Act agreements with us, and some other government agencies, for instance, USGS. And I don't know how familiar people are with the term TRL. It's technology readiness level. And it ranges anywhere from 1, which is really basic, like just concepts, to 9, which is flight systems. And in my group, we kind of cover the gamut. So we don't specialize in any particular technology readiness level. There are several research themes in our group. One is automated planetary mapping. So this is creating maps and terrain models of planetary surfaces from orbital assets. So we've done work mapping Mars, mapping the moon, and finally Earth. I'll talk a little bit more about that later. And then also geospatial data systems. So basically geolocating imagery taken from orbital assets. We do a lot of work on exploration user interfaces. So this is both from the standpoint of robot control and science operations. There is a bit of difference there, and trying to make the science data more accessible and geolocated. And then, of course, the robots themselves. So in particular, we've been concentrating more on robots for human explorers as opposed to the more autonomous robots like the rovers on Mars, although we have worked on that in the past. And we're looking to improve the efficiency and productivity of those robots. And they range from anything like free flyers, like I mentioned earlier, Astrobee, to lake landers, to rovers. We have a lot of collaborations. Some of these are more in the past, but some of them are current, ranging from universities to commercial entities to other government agencies. So just a little bit more detail on the type of robotics that we're looking at for human exploration. So we're trying to improve human productivity, mission planning and execution, and also to transfer some tasks to robots, especially those that are tedious, repetitive, long duration. And we're looking at multiple phases of the mission before cruise, so doing things like recon or scouting and prospecting, site prep, deploying equipment or assets, and then once crew gets there, supporting the crew. So either providing transportation, being a vehicle for the robots, for the crew, or doing supplementary tasks. So inspection and being a mobile camera, giving sort of like a third person point of view. And then finally, following up on crew after they leave. So gathering additional information, doing some closeout work. So for instance, we could do site surveys, with very tedious, repetitive measurements that crew really doesn't need to do. And then additional closeout. These are current robots, although I'm not showing one of the most important ones, which is currently being built, which is Viper. K10, I should actually say, is a little more retired, kind of on the out. We have a very interesting one there in the center, Super Ball Bot. It was called a tensegrity robot. So as you can see, it looks like a bunch of sticks and wires, but it's a novel concept. This is one of those lower TRL projects that I was mentioning earlier, where it's still very conceptual and working on prototypes. More of a workhorse is the K-Rex rover. We've done a lot of testing for the Viper mission on that rover. It's a very similar in size, so it's kind of like a small, very small car, like a smart car size robot. And then like a K-10 Mini below that, which is a little bread box size vehicle. And then, of course, the Astrobes, which are free flyers on the International Space Station. These are some of our labs. We have a hardware lab called the Rover Lab, where we have some machining capabilities. And then most of the rest of our labs are really computer labs, such as the Viper Lab, which currently is dedicated to that project. And then the Pirate Lab, which is really mostly a software workspace. We have a outdoor test facility called the Roverscape. It's a large dirt plain, basically, with a few craters and hills that give us some terrain to run rovers around. And we have a sandbox in there as well. And we have an ops trailer that we can actually run the tests for that outdoor facility. So some of the technologies that we work on are things like perception. So this is, allowing a robot to understand where it is. So different forms of localization and navigation. Also some specific imaging capabilities, such as high dynamic range or panoramic, which that Gigapan Voyage you see at the lower right takes panoramic imagery. User interfaces. So again, as I mentioned, it's currently somewhat split between what's more for rover control or robot control that you see on the left there, the Verve, and then more science operations like the XGDS or Exploration Ground Data Systems. And we are working to sort of merge those back together again. And then, of course, the software that's onboard software, like the rover software suite that we worked on, sort of back-end server tools, and then middleware like Rapid there on the right. So this Rapid, for instance, allows communication between heterogeneous robots and control stations. For instance, this is actually one of my all-time favorite photos on the lower right. It's from a field test that we did quite a while ago, where we had robots from 3 different NASA centers. So we have the, let's see, athlete. Can you see I don't know if you can see my cursor moving. Do you see that? Anybody?
No, I cannot see.
Okay, all right. I just wanted to point.
Okay.
So those kind of spindly legged things with the big bulbous thing on top, those are athlete robots from JPL. With a little habitat module on board. And then we see 2 crew members, 2 astronauts on basically a transportation platform from JSC. And then sitting right next to the taller astronaut is a K-10 robot from Ames. That you can see the ramp is currently deployed and the robot's about to drive off of there. And so, of course, at the time, we're all working on these very separately. So they had different operating systems, different control stations. And so you couldn't see one robot in another robot's control station. So we worked on this middleware that would enable us to command and monitor all the robots in all the workstations. We try to release most of our software as open source. So you can see here sort of some of the history of our open source releases. There's actually an additional one that's a newer one from a project called Isaac that I need to add to the list. But we'd like to get these out to the public. Hopefully, get more use in different agencies and academia. What's really interesting is this Astrobee robot software is in heavy use, actually, because Astrobee has become a facility on the International Space Station that external scientists and engineers can use to test out their technologies in 0G, so in microgravity. And so they can actually access the onboard software. We have a simulator, and they can actually run experiments in simulation before they then test it out, excuse me, on the actual robot.
Sorry, I just
Okay. All right, so now I'm just going to go through a few of the projects that we have going on in the group. Breeze, this is a fairly small project. It's what's called a NIAC, which is a program in the Space Technology Mission Directorate for very low technology readiness levels, so very much conceptual projects. This one is for basically a free flyer in the Venus atmosphere. And so we have a little bit of work in this, mostly in perception and navigation, kinematics assessment identification, and flight control algorithms that we would test out in simulation. This is actually one of the oldest projects in the group that's still going strong, because this software is open source and is used by geologists and so both academic and at the USGS. And so we continually update this software, add new features, but it's the AIM Stereo pipeline, or what we call it is the NeoGeography toolkit. And we've applied this, as I mentioned, to Mars. Also, we see some here from the moon. We're looking at orbital data and creating three-dimensional models of the surface. And then more recently, well, like in the last few years, we've actually started applying it to Earth. So working with Earth scientists now, looking at most recently on bathymetry. So actually using satellite imagery to look at the ocean floor in some of these shallow regions. And we've also looked at glaciation, sea ice movement, etc. We do a lot of work in extreme perception, especially currently we're targeting lunar South Pole for the Viper mission, but we're looking at different types of sensors that can be used to enable perception in these really extreme environments. So computer vision is kind of the main one, and optics, but we're looking at other types of sensors such as thermal, cold, and then looking at ways of deploying sensors in these extreme environments, such as projectiles, where you can send out a network of sensors into craters or caves. This is one of the larger projects in the group called ISAC. It's Integrated System for Autonomous and Adaptive Caretaking. And here we're looking at using robots, in particular intra-vehicle robots, which we term IVR, and integrating them with vehicle systems on things like space stations. For instance, ISS or Gateway, which is an upcoming station around the moon. And we know that for the ConOps for Gateway currently is to only have humans there, only have crew there for maybe a month out of the year. So most of the time there's nobody there to take care of the vehicle. So we're looking at how can we use robots to help to monitor and maintain these systems. And so we're actually using Astrobee as one of our test platforms for some of this technology. So I do have a video here. Let's see if it starts playing. So this is some of the work we've done recently on space station with the Astrobees. We see two of them right now working to map the interior of the station, so taking very high resolution imagery. And so here we have, you can see Queen, which is in the background in node 2 of the space station, and in the foreground is Bumble doing some actually navigation mapping, while Queen is taking more the high resolution imagery, excuse me, of the node. And then I think we have the next little segment that has both of them working on the US lab module. Here we go. So this is the two of them working together on mapping the US lab. We'll let that finish playing out. Okay. A smaller project again, that's kind of closing out, called Ocean Waters, is looking at creating a simulation test bed for some of these ocean worlds, Europa, Enceladus, etc., to try out new technologies for some future missions to these icy worlds. So we're emulating surface conditions. There's robotic manipulator operations, and there's actually a physical simulator that's being developed or has been developed by JPL that's also tied into this. So you can actually do some hardware in the loop simulations with the manipulator. And then we also test out lander systems in the simulation. A newer project is called Streamflow, and here we're working with USGS on mapping river flows. So you can see here we start with some thermal imagery, do some image processing, look at particles in there to map those velocity vectors of the flow of the river. And this is done with, as you can see here, the UAS. And here's the sensor package here. And then here's some of the recent data collecting testing being done in Sacramento, in California. And then, of course, the biggest project in my group that takes up about like 85% of my personnel is the Viper mission, which is the Volatile Investigating Polar Exploration Rover. And this is scheduled for launch in 2024. Our main role on it is software, mostly software, so onboard software, navigation systems, robot driving tools, some of the science support, and we also do a little bit of hardware on the navigation side. We're the ones speccing such things like the cameras and lighting systems for doing the sensing needed for navigation. And I think that's it, because that was alphabetical and that was V. So that's pretty much everything going on currently in the IRG. So, any questions?
All right, so we will go ahead and do questions like we've done in the past, everybody. If you want to raise your hand, go ahead and type it into the chat. And when we call on you, you can then hit enter. We'll read your question and we'll get through as many as we can here in this half hour. All right. I don't remember, somebody help me out, who's running the Q&A?
Yeah, do you want me to call them out or is somebody else gonna?
That was me.
Okay.
Okay, I see. We do have a question there, so I guess we'll address that one and I'll get to the list. So from, I believe it's Mishan, how do you access open source code to take advantage of robots on board the ISS for zero-G testing?
So it's on GitHub. I don't know how familiar you are with GitHub, but it's a public repository for open source software. So it's just a public website you can go to, and you can look up Astroby robot software, and you can just download it, and there are instructions on how to build and run the simulator. And then the way that you actually get to testing is generally so one of the main routes is that there is ASRI is part of now the national laboratory on the ISS. So it's an organization that you can propose to, saying, I would like to run these experiments. You have to describe what the experiment is, and then so you generally have to have your research has to be funded from whatever source, but then the national lab will then provide support for getting onto the space station, integrating with the robot and with the space station systems. It'll get crew time, like if you need to interact with astronauts on board, they'll supply the crew time. So it's kind of in-kind funding in some ways. They will provide support to get you integrated and running your experiment. But the research that you actually want, the technology that you're researching that you want to get on there has to have its own external funding. And it could be NASA funding. Maybe you won a proposal, that NASA had a call for, and so you have some other funding that actually lets you develop the technology.
Thank you. Next, we have Faith. So Faith, go ahead and send your question. When and how did you get hands-on experience with robotics during your time in college? Would you say it's vital to get a master's degree or higher for employment at NASA?
So in college, I actually didn't work on robots. I had sort of a basic electrical engineering education. So I mean, I worked on circuitry, certainly in labs. Actually, I didn't have I had one internship with like a telecommunications company. So internships are really important because they really do give you that practical experience and help you to understand like where your work fits into the bigger picture. So I did do one internship at a telecommunications company. I think it was after my junior year. But again, I was designing circuitry. It wasn't robotics really. And see, what was the second part of the question? Advanced degree. So no, it's not. I don't think it's vital that you get an advanced degree to work at NASA. We certainly do have some people who don't have advanced degrees in the group. I think it depends on what it is you're interested in doing. If you are very much interested in research, I think it really helps to have an advanced degree. But if you're more interested in like just getting things built, then I think you're fine with an undergraduate degree.
Okay, thank you. Our next question is from Angela B. But this may be one of the questions with a billion different answers. However, from a software point of view, what kind of problems had to be solved in order to be able to confirm that what the robot has sensed is actually water?
Well, so the thing is, I assume you're talking about Viper. For Viper, most of the analysis is not done, on the robot. It's done on the ground. So, and the instruments, the science instruments that are used to sense the water, are very much tested, and you understand what these signals mean that you're seeing. So, and I'm not a scientist, so I am an engineer, so I can't give you real details on how you understand it. But when you test it, you use ground truth. Okay, so when we're on the planet, we don't have ground truth, right? We just have our one set of instruments on there. So the term ground truth kind of means that you have independent confirmation, right, of what you're observing. And when we test these things, when we've been doing like all those field tests that we've done in the past, we usually have a suite of instruments on the robot. And we have a team of scientists, like say we're testing the robot somewhere in Arizona. We have a team of scientists at Ames, and they're using only the data that they get from the robot to make, decisions about what they're seeing, right? Making scientific evaluations. At the same time, we'll have scientists in the field taking independent measurements and making their own assessments. And then we compare the two, right? And so you do that on the ground, and you say, okay, it looks like our instruments are sufficient to tell us for us to be able to evaluate the situation. Then when you actually send your robot to another planet where you don't have ground truth, you have to kind of assume that you're understanding the readings correctly. So hopefully that helps.
I'm sorry, I muted myself.
Sorry.
So the next question is from Jesus Q. So Jesus, if you can hit send on your question. Are there plans for astrobees to map lava tubes in different moons? Also, what steps do I need to take from a community college standpoint to be where you are at?
So the astrobees only work inside the International Space Station. They actually use air to move. They need that cabin air inside the station for their propulsion system. So they're not going to be able to map lava tubes on the moon. However, we are looking at robots that might be able to do that. And free flyers are probably not an option. When you have gravity, it's hard to have a free flyer. And the moon, it's less gravity, but it's still gravity. So we're looking at things like little rovers that actually can go down into the tubes, or if you have what's it's called a skylight, where say a section of the roof of the cave has fallen in. So we're looking at things that can rappel down into a skylight. So you might have a bigger robot on the edge, with a tether that can lower something down into the tube. Or if there's an atmosphere like on Mars, you could have a free flyer that's really like a drone that could fly around, like Ingenuity, like a little helicopter that can then fly into those tubes. So let's see, second part of the question was community college. So I would say the main thing is just, taking that coursework that gets you towards an engineering degree. So I think from community college's standpoint, that would be like the introductory science, like physics, and then the math, or if you're interested in software, the program, there's plenty of programming you can learn. In fact, that's where I learned programming. Actually, I took a programming class because like I said, my background was actually in hardware and electrical engineering, but my division was doing all the software. So I took a C++ class at my local community college to start to get into programming. So that's the main thing to do.
Thank you. Okay, next question is from Samuel H. What tech might you use to test the habitability of a lava tube?
You'd probably want some radiation sensors, because that's one of the main reasons you'd want to go into a lava tube, because that's more likely not to be irradiated, and you're more likely to find past or extant life in a lava tube. Also, if you're considering it for habitability for humans, for say a lunar base, you'd want to check that. Let's see, you probably need, so obviously you're going to need lighting, right? Because you don't have sunlight in the tube. Let's see, what other tech might you need? I think that's kind of that's the sort of sensing that you need. For navigation, you'll need either need to bring your own light, if you're using cameras, or if you want active sensing, you can use LiDARs, for instance. So a laser radar that gives you volumetric, gives you distance measurements. Yeah, I think for lava tubes specifically, that's what you need.
There is Jaden K's question. I know he was up next. So how does the Viper transmit data collected from volatiles on the moon? For example, collecting a sample from the, I probably can't say it, Cabeus proper crater on the south pole of the moon.
So for Viper, we have direct to Earth communication. So that means that we're not trying to bounce the signal through like a satellite either. First of all, we don't really have them around the moon, and we're not trying to go through any kind of Earth orbiting communication system. So it's a ground-based telescope is going to have to is the way we communicate. We have to point Viper has got a directional antenna that's to point towards Earth to hit a ground-based telescope that will enable the communication. Let's see. Yeah, so the nice thing about the polar region for the South Pole and the timing of this mission is that we will have line of sight to the Earth the whole time.
Okay, thank you. And next is Edwin. So Edwin, can we see your question? How did you deal with signal interference from external factors such as radio waves, vibrations, etc.? And is there a way for us to access the data you obtained from the projects?
For some of them, yes, they are publicly available. For most things that are NASA funded are publicly available because the public is paying for it, right? And so we have to make that data available. So there are data sets available. So depending on which project or mission you're interested in, there are repositories for that data. Let's see, signal interference. I'm not quite sure in which context you're asking. I mean, there's always going to be some noise, right? But and I'm not a comms expert, so I can't really tell you exactly how, like, we deal with deep space network communications, to Mars.
Okay, thank you. And next we have Connor. In terms of general robot capabilities, how complex would a task usually get before it is more beneficial to have a human gather and interpret data or to complete a task? Also, how does the vacuum of space affect the behavior of electronics?
Okay, so I'm assuming for like planetary exploration, you're talking about that robotic versus human exploration. And I think the main thing is that it's just so expensive to send a human, just because, of all like the life support and, the considerations, you got to keep those humans alive. Right? And so there's certain, there's the envelope of what would be a safe launch, landing, all that is smaller for sending humans. And so just the technologies have to be just that much more robust and capable. So it's a much bigger proposition to send humans. So there's definitely things that we probably could learn better and faster if we send humans, but it's a little bit cost prohibitive, especially for these more outer planet type missions. I mean, we would like to eventually get there where we can send humans, but at the moment we can't. And also there's some technology still that we don't quite have, right? That can really send humans safely. So like landing on Mars, right? We just barely are able to land, like a 1-ton payload, to Mars. So and human systems are going to be much bigger. So there's still a lot of technological work that needs to be done before we can really contemplate sending humans. And then what was the second part of the question?
How does the vacuum of space affect
electronics? Okay.
Yes.
So obviously there's much more extremes in temperature. So, and there's often it's not the extreme of temperature if it's a constant. It's the extreme of it's the changing extremes of temperature, right? Because it's the cycling of the temperatures that put the strain on the joints, right? Your solder joints, right? So it's really really, you have to consider things like warm electronics boxes, right? Webs like they have on the rovers on Mars. So temperature is a big one. Vacuum, there's some considerations there, but generally, electronics can survive vacuum. Let's see what else. Radiation. That's actually a really big one, is radiation. So for instance, the Astrobees, we have some SD cards on them. And we've already, and we have them also in its docking station, right? There's like a docking station where they can fly up, plug in, and charge up. And so far, we've had 2 SD cards on the docking stations get knocked out by radiation, and one on one of the Astrobes has gotten knocked out by radiation. So, you know, electronics are very susceptible to radiation. So that's actually a really big one. You can deal with temperature extremes, you know, like I said, you keep the box warm. It's the radiation that's often the problem. And that's also why a lot of the processors that we see on space systems are very low tech, right? They're very old processors. And part of that is because they have larger transistors on them, right? Which actually survive radiation hits better than the tiny, the really small ones of a modern processor.
That is interesting. Okay, thank you. Next is Daniel Sandoval. How exactly are the Astrobes able to move freely? I didn't know NASA had those types of robots working on the ISS. I think it's amazing. I might switch my major. On programming for these rovers, I notice you use, I guess it's SQY-Lite. Are you primarily using it to save data?
Hang on, I'm just typing in Astrobes website. There we go. Okay. Sorry. SQY-Lite. I'm not familiar with that. I'm gonna need some help on what a SQY-Lite is.
Not sure.
Okay, but I will answer the question of how the Astrobes move freely. So as I mentioned, they need air, right? They need to be inside a cabin of a space station or a vehicle. They have 2 impellers on either side that draw that ambient air in and lightly pressurize it. Basically, it's like a little box on either end that we're pulling in a little bit of air, and it's just a little bit of pressure. It's only like 0.1 psi over the ambient. And then there are nozzles with flappers, right? And so they're continuously controlled. They're not just like bang bang. So you can open them partially if you want a little bit of air coming out, or you can open them wide to get more air coming out. And so that's how those are the nozzles are how we push the robot pushes itself around inside with microgravity, it doesn't need to lift itself up off like a table or a floor, so it doesn't need a lot of pressure to be able to move in any direction. Oh, C language library, is that what SQLite is? Yeah.
Yeah, well, I guess
so we do
SQLite.
most of the software that we write is in C or C++. That is true. And for robotics, what we're trying to go, if you're at all interested in this, we're trying to move towards so there's a software environment called ROS. It's Robot Operating System, and a lot of universities and government agencies and NASA, we all use it as part of the onboard rover software, and we're trying to get it more qualified for flight as well. So we're trying to get a standard for that to make it a more it's called V&V, verification and validation for flight. And that's also mostly in C++.
Okay, thank you. And next we have Avadi. I can imagine that accuracy is a big part of your work. Do you have any correction algorithms such as PID at work during autonomous tasks?
Yeah, PID is kind of in the lower level of a robot, mostly controlling the motors. So for instance, the wheels or the arms or the various actuators, right, on board a robot. So for instance, on Astrobee, you have a sort of motor controller for pretty much every actuator, and then we usually run a PID control loop on that to actually control the motor for instance, opening the flaps, right, of the nozzles, or controlling the speed of the impeller that draws the air in, right.
Okay, and next we have Kenoa. I hope I pronounced that correctly today. see. Do you have any advice, guidance for someone who wants to get into programming, robotics, and analysis software like those talked about today? I'm a comp sci major and I'm very interested in working in this field, but I'm very much a beginner when it comes to programming. I have no idea how it would work towards my goals.
Well, so as I mentioned, we do tend to, for programming language, C and C++ are kind of the mainstays, right, of it. But I mean, so object-oriented programming, right, is one thing. Understanding, algorithm development is very important. So math is also very important. Let me think. I think like a standard computer science degree is a good way towards that. You might want to look at some like lower level of programming as well. For instance, if you are really interested in working with the hardware, as opposed to like the autonomy and higher level thinking on the robot, then you might want to look more at like microcontrollers. Programming microcontrollers, if you're hardware, but if you're interested more sort of in the higher level computation on the robot, how it navigates, then it's more about like algorithmic. For instance, there's simultaneous localization and mapping, SLAM, right? So look at those sorts of algorithms. Or then there's even higher level of planning, right? Of mission planning, motion planning, right? And so there's so that's more kind of AI, which honestly, I don't understand a lot about that. I didn't get that far in my programming, but there are different languages also that help with that sort of higher level thinking, right? For programming, things like Lisp, right? I never learned to program in Lisp, but I think for more from like the hardware kind of infrastructure level, it's those object-oriented sort of C++ type programming languages. And then for higher level kind of decision making, it's things like Lisp. I think Lisp is sort of I don't know, that things may have changed from when I was first learning computer science to, they may use different languages now. I don't know.
All right, thank you for all that information. Next, we have Keela. So Keela, go ahead and hit send. First of all, I want to say you're really personable and awesome. Secondly, I'm not sure if you can answer this, but with the water sensor, do you calibrate instruments beforehand so that the robot recognizes the compounds and relays information as water, similar to like a pH lab Quest probe or something?
Absolutely. Yeah, all the instruments have to be calibrated. I'm not sure how they, if they have to recalibrate instruments like, let's use like a neutron spectrometer, right, for water detection. But things like cameras sometimes will even send a calibration target on the robot itself, so that after it launches, we can make sure that the cameras stayed calibrated after all that shake that it experienced on the launch, right? So there might be like a little calibration target on the body of the robot that you can turn the cameras to and point it at to double check that those cameras have stayed calibrated through launch, or to recalibrate.
Okay, thank you. Now the next question is from Garrett. I know we have two more questions. I'm going to try and get them in here. Okay, Garrett, go ahead and send it. And Alan, go ahead and send yours too, so we have them both in the chat. Okay, forgive this being a silly question. Where are we getting the recording? Okay, that's one of our questions. We can answer that one. Okay, Alan, there's one project you mentioned which uses Python Django for UI. Is it open source? If so, can you share the GitHub link for it?
So we use Python and Django quite in several projects. I believe actually we do use it in the Asterby open source, and possibly also on some of the Isaac work. I don't have like the GitHub. Like I said, if you go to GitHub and you look for Asterby, you should come across it. I don't have the URL handy. And also, as I mentioned, there's the Isaac work as well. That's also on GitHub.
Okay, and I know our team member Ashley shared a github.com NASA site, so hopefully they could find it there. And I want to thank.
There we go.
Let's
Somebody
see.
put it up there. GitHub NASA Asterby.
Yes. Okay. And I don't know. Well, we're about out of time. So, Sarah Beth, did you want to close us out? Thank you for answering all of those wonderful questions.
You're welcome.
Thank you so much, Maria, for coming today. It was awesome to hear about your background and all of the different robots that you've worked on, and just hearing your knowledge. I know it was really inspiring for the students, and I'm blown away by all of the work that you do and how much you know about all the things that you work on with the robots. So thank you so much for sharing with us today. And I really appreciate you coming to speak today.
You're welcome. It's my pleasure.
Okay, I think we will close this out. I hope you all enjoyed the presentation today. The recording will be available later today. And we are looking forward to seeing you for your next session later.
Hi, Sarah Beth, before you go.
Sure. Hi, Danae. How are you?
Hi, how are you guys? Hey, listen, sorry, things are ringing around here. I'm sorry. I didn't want to miss the opportunity to make the connection between Maria's presentation and the fact right now that we currently have a opportunity on the street for students to join something called the Kibo RPC, which is the Kibo Robotic Programming Challenge. It
Yes,
is
on Asterby.
on Asterby's, yes, that is run out of the office here at JSC. And I'm just reading from the flyer here. They're looking for high school students enrolled in the US or undergraduate students enrolled in US 2-year or 4-year higher education institutions. And so they're looking for students who want to program the Asterby's. I understand that this is a competition, it's a global competition, but the US team and the management of the US team happens out of Johnson Space Center. I would love to see some team from NCAS actually participate in this. So I'm gonna make sure that I flag this for the manager who's actually overseeing this. His name is Jamie Simple. And I also encourage you guys, since this is such a topic that you guys have been demonstrated interest in, I do realize that the US team, the winning US team might travel to Japan for the international final round. So that's another incentive that you might want to consider as you are formalizing teams. My hope is that this career simulation puts you in the space and feeling of actually working at NASA. And this is a nice follow-on activity to go along with it. So look into it. I'm going to put the link. I'm going to make sure Selena and the team has the information so that you guys can look into it, and so that this can be shared with all of the students who are participating, who have participated in missions 1 and 2 this year. Thank you so much. Thank you for letting me take that time to say that.
Awesome. Thank you so much, Danae, for sharing that opportunity. I'm already seeing a ton of interest in the chat. So I think that this is going to be a really awesome opportunity for some NCAS alum to join this. So I hope that we can see some teams from NCAS in there, and thank you for sharing. All right, with that, I think we will close this out. Thank you everyone for coming today. And big thank you to Maria for sharing your story and your background with NASA.
Thank you, everybody. Remember, office hours start at 1:30 Central Time.
See you all then.
Bye.
Thank you.